Okay, so this is a completely different talk. It's about the upgrade to the JLEIC design. As the base shows, there's a report from the National Academy of Sciences which spells out certain requirements for the electron-ion collider. So root S between 20 to 100, upgrade to 140. Ion beams from deuterium to heaviest stable nuclei, 100 to 1,000 times their luminosity. I will discuss this, what this means a little bit later. And at least 70% polarization for electrons, protons, and ions, 1 or more hour of individual acceptance. So, this is an update. So you are the first audience, I believe, who's going to hear this. So the fundamental concept is unchanged. We have a written report in 2015, which is updated to 2017, and this is this update. The document is not quite finished yet. It is under development. So the idea here is to increase the root S range by increasing ion dipole rings from 3 Tesla to 6 Tesla. Keep the footprint of the design the same. The luminosity performance to satisfy the requirements that we saw before. And IR retains high acceptance, polarization remains high, with 4 relatively small design changes. So we will, by going from 3 Tesla to 6 Tesla, the electron ring stays the same. We will increase the proton energy range from 30 to 200 GeV. And this should be upgradable to 400 GeV. We use the high energy LHC or HCC dipoles, which is being developed now. The assumption here is that the upgrade will take place quite sometime after, obviously, the construction of EIC, which would be getting on towards 2040. So this puts the Jackson Lab EIC energy 20 to 100 GeV, upgradable to 140 GeV. Most of the design remained the same, as I said. Electron complex is unchanged. Ion complex is mainly incremental change, the biggest one being this 3 Tesla to 6 Tesla. It has pre-integrated high acceptance IR. This is being reoptimized for high energies. And at the moment, we're working with 2 IRs with the same acceptance. It has DC and cooled beam, bunch beam coolers. It also has incremental changes, but we add here a no bunch beam cooler concept. So high luminosity is achieved using multi-phase cooling. So there's 2 kinds of cooling: DC cooling and bunch beam cooling. I understand mostly theorists. So DC cooling is sort of a known technology. Bunch beam cooling is kind of still a lot of. So the DC cooling, a lot of it exists. It does push technology a little bit. The 3 MeV DC cooler, this pushes it to 6 MeV. The DC cooling is used for emittance reduction. Bunch beam cooling is really used for emittance conservation against intrabeam. The bunch beam cooling has not changed. It does push the parameters a little bit more than before. And the figure 8 is the same. So the figure 8, as you may or may not know, is there to preserve polarization. So the idea is very simple. Instability is going that way, cancels instability is going that way. You may or may not know that the person who actually invented this is the same person who invented Siberian snails. So there are several, I guess 2, 3 experts, and theoretical experts in accelerator science will work on this kind of thing. And Slava Durganev is the inventor of this particular. So the important thing for you is that this preserves the polarization of proton-like ions, including deuterons, and electrons at greater than 80%, therefore also satisfying the requirements that we stated earlier. So now I'm going to talk a little bit about luminosity and what it means. So the NAS report said 100 to 1,000 times the error luminosity. What does that exactly mean? So This is Hera luminosity, delivered luminosity per days of running. This is Zeus. And you can see that it delivered about 600 inverse picobarns over 1,000 days of running. This means that Hera delivered something like 0.6 inverse picobarns per day or 4 inverse picobarns per week of integrated luminosity during running. There were 2 collider experiments, so I'm going to inflate this to 6 inverse picobarns per week. And the real reason, of course, is that if I make it 6, everything turns out to be wrong numbers. So you can blame this in the Babylonian. Okay, so 6 inverse picobarns per week divided 1 week in a second is 10 to the 31 square centimeters per second. This is the average luminosity of Hera while running. So that means that if you have 10 to the 31, if you run for a week, in real world conditions, you get 6 meters. So we'd like 100 to 1,000 times Hera luminosity. So the aim is 0.6 to 6 inverse femtobarns of running, or average luminosity while running of 10 to the 33 or 10 to the 34. Okay, so 6 inverse femtobarns per week is 100 inverse femtobarns per year, assuming 10 to the 7 seconds in a year. So this is the annual mass here. This is 1/3 of the year. So average luminosity while running is quoted for Jacobson value IC. So I want to emphasize that operational inefficiency is already taken into account. I mean, you can actually take the number, efficiency, average efficiency, and multiply how long you think you're going to run and get the integrated luminosity. This is a plot. 1,000 times Hera 10 to the 34 is here. 100 times Hera 10 to the 33 is here. 100 inverse femtobarns per year, 10 inverse femtobarns per year. So this is the curve that you would get with both DC and bunch beam cooling. However, we can also dispense with the bunch beam cooling and still get very good luminosity. So luminosity is 100,000 times Hera over the energy. This is also so with the upgrade, the luminosity curves look like this. Of course, this is a lot more assumptions built into that curve. If you look at the amount of luminosity which is actually discussed in the white paper, divide this up into EP low, EP medium, EP high, phase 2 at 140 GeV, and deuteron or light ion, calcium, and heavy ion. You get a table like this. See the references. If you add this up, it's something like 640 inverse femtobarns. And as we discussed before, 10 to the 34 will give you 6 inverse femtobarns a week, so 100 inverse femtobarns. 10 to the 33 will give you 10 inverse compared to this kind of number. So this is a summary. The basis of the design, the ring high luminosity with high repetition rate, high polarization, full event coverage, and technical risk has remained constant, I guess, since 2003, as the page just pointed out, not 5. The energy reaches 20 to 100 up there to 140. Design delivers average luminosity as opposed to 10 to the 30 to 34. In the entire energy range with only DC cooling necessary. Achieves 80% polarization, greater than 80% polarization for large ions, including deuterons and electrons. Pre-CDR with full description is under preparation. There may be minor changes to the parameters upon its release. The overall design risk is low. Technology demonstration is mostly needed for the bunch beam electron cooling. However, very good performance can be achieved with entities. Thank you.
Okay, questions 3.
I didn't catch what happens with heavy ions. With heavy ions, gold.
They work fine.
Yeah, well, I didn't see it on your paper, so the velocity
Oh, the luminosity is essentially the same.
is what?
It's essentially the same.
Okay.
So you want 640 inverse. What's like that?
Yeah.
If you might.
Yeah.
Yeah, thank you. So as you know very well, of course, some of the things can be measured at the same moment. I don't have to measure gluon spin separate for TMDs with longitudinal.
Yeah, this was taken into account. So anything in the brackets can be done concurrently with the other measurements. The other ones cannot.
Okay.
Yeah,
I'm a bit surprised because I did a similar exercise and I didn't come up with this, but you took also, for example, for DVC as a 100 inverse femtobarn, which is only for some measurements.
Yeah, so
for
what
some
I did,
special spin. But okay, so you took this already into account. That wasn't so clear. Okay.
Yeah, so what I did also was to add the transverse one, which is
if you do NT, you need a yes.
Yeah, so I doubled that at one point.
Which of course you can always average out the L and then you get only transverse. But okay, fine, you already took something like this into account.
Transfer spin, you need a transfer spin separate.
So
this is transfer spin or longitudinal spin.
But sometimes it's a single spin asymmetry, you know, when you need only UT. Okay, it is already taken into account. That was my main question.
So the other thing is, I do assume that unpolarized cross sections can be reconstructed from polarized ones.
Yes, absolutely.
Which is not completely obvious. If you have to measure, the uncertainty that you buy by having a polarized beam is
you have to average out your polarization very well, and you have to make cuts.
Yeah. So it's not completely obvious, but I'm assuming that can.
Question.
Since I will be talking a little bit about the threshold region to produce epsilon,
yes,
for discussing the mass.
Yeah.
I was just wondering whether the luminosity reach that you have at the low center mass, or that's between 20 and 40, whether there is any hope that you can actually get it a little higher.
Here.
Yeah. So that
well, yeah, I think things do become difficult now because of the lower energy. So we do think that there is a very good chance that this will at least be here. So we think there's no real showstopper for the expansion.
There's some people talking about mitigation of space charge effects at lower energy, but then you really have no territory, so I don't think anyone really knows. A lot of people will looking at it. That's the problem. You have to find a scheme model to mitigate space charge.
Of course, doing the JLEIC threshold at these energies is very tough. The best, Quarksian to work with.
Yes.
And of course, as you know, the cross section then drops by another factor of 10.
Yeah.
I was just wondering what is realistic in that.
Yeah. So there are multiple effects that you have to factor. Space charge being one of them. But I think we can take a look at that. But I think there are.
Like somewhere around 25, how much can we go up?
Well,
you get to 34, I know. Otherwise, you can't get enough content.
well, I mean, I think the thing is you can probably get it up, but then you have to change other things about the machine, which may not work as well in other areas. So that's the trade-off.
So is there like a special tool that we could be running at some point just to beef up the luminosity there?
One thing you can do is change your electron energy, so you can always go to the lowest electron energy. But there also, in any given area, how low can you go? So most of us say we don't go below 3G. There's more than 3G in play. Some levels still arbitrary.
And then 3G, if you want to see those kind of leptons, as we discussed in your detectors, that is a major challenge because with one detector to have the same response is kind of really tricky. So
there's ways.
Yeah.
That's the problem.
absolutely. Yes.
Yeah,
I'm thinking running with high electron energy, meaning 10 GeV.
well, and then the ion becomes interesting. So also, so there are effects of not really being at the speed of light, which begins to actually affect the timing of the machine itself, which is kind of a difficulty at that end for ions.
Thank you.
Can I change to another topic already? Are people done with this? I would like to go to the science piece.
Sure.
I have a question for that.
Actually, we're very happy to hear any criticism.
No, I actually want to ask something about the science piece. Is there any way how we can better fold in the use of spin? Because the problem is more or less, yeah, there's great arguments.
The use of spin.
That's correct.
Or
Is something
something
that's, yeah, why essentially, if you make a comparison with X-rays and you look at the image,
Yeah.
you get this whole spiel of, and I think we can argue to go to the femtoscale easily.
Yeah.
I think that's a good argument to get there. I think you more or less can, because the argument to use nuclei is also relatively simple, because we want to look at nuclei at the femtoscale.
Yeah.
But then the question is still like, okay, now why do we all argue about polarized collider? So it would be nice if we have some simple examples why say polarization helped in the past. Follow that a little bit more in the global story.
Yeah, right. Of course, in this story, in that story, polarization is obviously important. Obviously, maybe, but the fact that nucleon-nuclear interactions are a certain way and how they come together is obviously important. Spin as well as all the other characteristics.
So you want to flush that out
I
more?
think so. Good
Yeah.
question. Like, it's true. Then you might be able to point out that to the spin part of the interaction that we have. If you wouldn't have a spin piece of an interaction, we
No,
would
I
have
think
bound
you're right.
neutron or whatever. But somewhere then the spin comes in.
Yeah.
That might be
I think
useful.
that's a good suggestion.
And I think there you could probably make a comparison to neutron scattering, right? Which is really sensitive to the magnetic properties of the material. Whereas photons are not so ideal in that respect. Whereas on the Gluon level, relativistic, there's no difference, right? So you can do both at the same time. That's a big difference.
There's this famous, quote by Bjorkane that says that spin has killed more theories.
And then
Particle
than
physics.
any other single
Than any other single
parameter.
period. So we have a list of those kind of experiments.
Okay.
Sorry, but
Just one point about this advertising the spin, since you are speaking about getting to this work level, means the manipulating to some extent, means that you have to understand orbital motion. And orbital motion, spin is the way to understand orbital motion. Maybe in that way it can enter the game, then it will be a lot more clear. Without it, it will be much harder.
No, I think these are good suggestions. We do only have 3,000 words. So.
No, but it's probably true that if you go to your atom, there you have more or less that structure and interaction are separate. That's not, so that's the way to do spin.
Yeah, right. I wasn't supposed to do that. Sorry.
No, that's fine.
First the wrong button.
Just push the same button.
Just the way to correlations between atoms. Spin is a way to measure correlations between. So,
Yeah, no, I think we can do that. Yeah.
okay.
All right. Let us thank Rick once again. We have 25 minutes to have coffee break and start now message.